All right. Hello. So my name is Joseph. I'm the former captain of Gatorbytes, and I was the lead engineer on our world's winning robot. And I'm going to be outlining just a few of the tips that we've figured out over the years from the small little things that lead to large advantages on our robots throughout the season. And so KISS is a design, not just a process, but also an idea and a method that engineers could use. Um, and what KISS allows us to do is allows us to build robots in a way that they're much more reliable. And because the way FTC runs with ranking points, as well as two loss elimination, is really important to be consistent throughout an entire competition. So what is KISS? So KISS stands for Keep It Simple, Stupid, and it was coined by Kelly Johnston. He was one of the lead engineers at Lockheed Martin and helped develop U-2 spy plane and SR-71 Blackbird. So he's a very renowned engineer, and he did some amazing things pushing forward technology. So um, why do we use KISS and FTC? So one of the things of why we use KISS and FTC is because of reliability that we can get through our robots helps us do well in better competitions. Faster design processes, which allow us to have robots earlier on in the season so we can continue to iterate throughout the season, creating more optimized designs. We have more room for high level optimization and engineering. And we also get benefits in the judging room. So high reliability. So one of the things with KISS is that simpler subsystems are much easier to design um, and assemble for most teams. Some teams can really pull off really complicated designs really, really well. But for some teams, it's better for them to pull off a simpler design and do a lot of the engineering behind it to a really in-depth way. And simpler components are more likely to have less uh, overlooked features. When you're designing a really complicated part, if you overlook one joint, could be hit in just the wrong way in a match 2 months later and break. But if you have simpler parts, it's much less likely to fail. We had that happen a lot on our freight frenzy robot. It was too complicated and it broke too much and caused us many problems at competitions. So we tried to fix that this year. And less moving parts means you're using there's less points of failure. And overall, just having less points of failure creates for a much more reliable system that your robots have. Um, So faster design process. So simpler subsystems are much easier to rapidly design and iterate upon. So when the season just kicks off, we hit our whiteboards, we design all of our stuff, we draw it out, and then we start rapid prototyping with all of our parts. We start building, 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 building. Really complex systems, hard to kind of build and test without doing a lot of the engineering behind it. So we offer simple systems that we can test a lot and see what works, what doesn't, so that when we go to actually design and develop our final iterations of these robots, we have all the experience for them that we need. Um, More optimization. So if you have a really, really large component, so you have three linear slides and a bunch of claws, 6-axis arm that can do all this differential stuff, to pick up cones, for example. It's really, really good, but it's also really, really bad optimization wise. Because it's really easy to optimize a simpler system. So on our pass-through robot, we were able to optimize not only the pass-through arm, but the claw and lift to basically as far as we could go. So if you like graphed out our max potential, we were within about 5 to 8-ish% of that. And that's something that just is really, really important to have is maxing out the potential of your robot. If you have a really complex robot, it's much harder to optimize and maximize your capabilities. Whereas with a simpler robot, you can do all your really in-depth optimization and fix any sort of things to make it run much better. Judging advantages. So at least in SoCal, where we are, the judges really, really like it when teams explain the full engineering of a part start to finish. So there's some teams that'll show up with like a differential sort of drive, but they struggle to explain how they 3D printed it and how they designed it, developed it, and engineered it. And the judges give them credit for having a really cool design, but they mark them a lot for not being able to explain their ideas. Because in the end, first, it's about learning things. And if you're not able to explain what you've built, you're not really learning anything. You're just building something. And by learning, you're truly able to explain anything you've built. So our team tries to build things that are follow the KISS design process because we're able to explain it in a much simpler manner to the judges, which they tend to like. How did we use KISS on our world's winning robot? So we basically sat down at the beginning of the season and you decide to use KISS from the very early stages. But then when we were going through our development and writing our engineering manifesto for our Artemis platform for regionals and worlds, we basically decided that every single part had to be perfect because closer it was to perfection, um, the more reliable it would be and the more points we could score, which in the end, that's what wins us matches. So we basically had four main components that had KISS applications, mechanism drivetrain, drawer sled lift, pass-through scoring arm, and our Gecko grip claw. So the first thing, our mechanism drivetrain. In previous years, we've had odometry that can be lifted up by servos. We've had fancy belt systems, gears. This year, we just went probably one of the simplest drivetrain possible. So it's just motors on group mounts that belted out to the wheels. And the reason we did this is that sometimes we've had problems with motors that will either burn out or get loose over time, even though we've Loctited them and everything. So to make it easier, we can just unscrew. It's 6 bolts. We can take the entire motor thing out, tighten everything back down, and put it back in. And so we just do this because not only is our upkeep faster, but if something goes wrong during a match, we can have it fixed within about 5 to 10 minutes rather than 20, 30, 45 minutes, which could take us out for a match at a competition. Our drawer slide lift. One of the questions I get asked a lot is how we made our slides so efficient. And one of the things I say is lots of testing. So the number one thing we did to our Mizumi drawer slides is we took the slides, we cleaned out all the grease in them, and we put white lithium grease from Ace Hardware in them. Because white lithium grease was much more efficient and it made the slides smoother and faster. And we could drive them with much less friction, and it was just overall much better for us. The other thing we would also do with that is we take a look at our slide mounts. We just use simple 3D printed mounts. We did no fancy um, metal mounts or like clips so that would extend the first stage first. We didn't use any linear rails. We just used drawer slides because we wanted to stay light, simple, fast. And then to mount the slides, if you ignore the bolts used, we only have 7 parts that our slides are mounted to in total on the entire portion above our turret. And we're like, how can we minimize the amount of parts we use while still maintaining absolute strength? And so part of that is through some of the go-built mounts that we were able to find, as well as our pocketed plates. So our pass-through turret arm. So the pass-through arm was a late addition that we added between regionals and worlds. And the reason we added this is because we saw what teams like Terabats and Brainstormers were doing in auto and teleop, how they had advantages of both. And so we saw that our turret design had room to do both, have both advantages of their design while not having the drawbacks from stationary robot and for having to get close to the center line because of our turret. So we were able to optimize the pass-through arm, go from grabbing position to scoring position in like 0.3 of a second. So it's really, really fast. You don't run it at 100% power most of the time because sometimes it's so fast it will like flip cone out of its claw, and that's a mistake, and we get penalties. So we run at about 80% power, but it's very, very fast and it's very light. So our claw. The claw is one of the things we spent the most time on this year. We've had the most issues with. And that's because we chose not to use Claw from the very beginning when it was released. We're not going to use an open source claw. We're going to design our own because we pride ourselves in everything's ours. We don't outsource any design to anybody else. We don't use open source parts. We don't use open source code libraries except for Roadrunner, which is heavily modified for us. So we basically written the entire following algorithm. But for the claw, we had issues with slippage and breaking snapping. And we even had a part that we had left on the claw that on the way to World snapped because Southwest Airlines decided to throw a robot. Um, but we had replacements for it that had fixed, so we just popped an entire new replacement part on it, and it didn't break again. And one of the things we just learned from this is the claw uh, was our intake. So because we didn't have to optimize an intake this year, we had to optimize our claw. And so some teams had much wider pivot points. So they could pull cones away from the wall when they were grabbing, especially in auto. I know teams such as Wolfpack Machina and Don't Blink had similar designs, but we chose not to go for that design because it's much wider, it's much bigger, it's much heavier. So we made this really, really thin and light design that is basically weightless on the end of our arm, which also reduces our overall lift weight that has to be extended, which allows us to extend our lift in under half a second when running at full power, which is just one of the things that we've used KISS throughout the entire design process just for speed and reliability. And we've had issues in the past because of our lack of adherence to a design process, because we're jumping around between complexity and simple and CAD and no CAD and hand machine parts and laser cut parts and 3D printed parts. We never committed to one set ideal of design. And so KISS is what we decided to use this year because the game was fairly simple. So we're like, robots should be simple, it shouldn't be complex. We shouldn't make anything. The saying goes, if the biggest flaw of an engineer is an engineer engineering something that shouldn't exist. And our team always is looking at our robot saying, does this have to be here? And we even looked at our turret at one point saying, should we remove this from walls? We ended up not, and it ended up being a huge advantage because we could stay away from the center line. But we were even looking at removing that because we just want to stay simple. We want to stay as reliable as possible. The more parts that have the opportunity to break, it's things that will happen, can happen, will happen. And if things do break, it's downtime. It's less matches you can be at full power in, score less points, and the ranking points are at the end are what are most important throughout qualifications. So, is there any questions?
There's one on chat. So it asks, what's your Jason Doe asks, what's your pass through on continuous or set position for the servos?
So the pass through, it's on set position. So we just have basically in a 3D space, we have multiple points that we're given based off of where the junction and our robot are. So in auto, it's completely different. It's a whole custom algorithm. But in teleop, basically what we're doing is we always know where the point of contact with the junction is relative to the top of the junction. And so that we just set a go position to our optimal scoring placement. And if you watch our scoring, we're only about an inch or so above the junction when it comes over, and we drop it down at least really fast. And that's all done just because we want to be able to have just as simple as possible, just like 4 or 5 set positions throughout the entire movement path. And also because it's where a robot's more stable. If the arm's vertical and moving around while it's vertical, our entire lift has more weight higher, which is just slightly less stable when driving around.
Anyone in person have any questions?
I asked the holiday base. What process do you use to grease out student slides?
So the grease out of the Mizumi slides. So that's the second most question I've had about our slides. We had a lot of regionals.
Please say you used a power washer.
Well, we used a form of a power washer. So we had a leftover dental water pick.
You really did.
So we used that to clean out the major chunks.
Okay.
And then we used some acid solutions to go through and just clean it out and just run it through just keep running it through with water and acid, and it
This is Olivia.
got it all out and put new grease in and it worked perfectly for us.
That's fine.
Okay.